Hi, my name is Naruya Kondo from University of Tsukuba. Let me introduce our work, Immersive Real World through Deep Billboards. Let's think about how to bring them into virtual reality. The VR industry has been growing rapidly in recent years, and many real-world-based VR applications such as virtual shopping, showrooms, and telecommunications have been developed. They are creating a new lifestyle for us. The aspirational goal of VR is to ruthlessly bring in diverse types of real-world objects into VR. However, despite the recent developments in deep learning, we have not made much progress on data-driven replication in VR. It is still challenging to bring objects with rich texture or moving objects as they are. One of the most popular methods to replicate physical objects in VR is photogrammetry. This method is commonly used in 3D modeling work these days. However, it cannot capture delicate shapes, such as hair, transparent areas, or view-dependent appearances. Moreover, it cannot capture objects with few visual features. On the other hand, recent deep learning methods such as neural radiance fields or NRF can capture objects with high accuracy and generate images from any viewpoint. NRFs and recent deep learning methods are not restricted by mesh or other explicit data representations, so they can directly optimize the appearance. We trained this NRF model with only 38 images. It's very powerful. These are some objects rendered by implicit data representation-based models. They are highly photorealistic and reflect the various textures very well. However, have you ever seen this technology in VR? I think almost everyone would say no. This is because, unlike mesh, this implicit data representation cannot be used directly in existing graphics pipelines. Let's briefly review implicit data representation-based models. These are basically image or video generation models. When given a certain viewpoint, they can predict and generate observations from that viewpoint. Unlike mesh, which is represented by a surface and texture, it does not have an explicit three-dimensional structure as the name implies. Several previous studies have attempted to convert NRF to mesh or point clouds, but the appearance is clearly worse. Data-driven learning can learn the correct appearance, but it cannot perfectly reproduce the density, and small density errors can cause the appearance to deteriorate significantly when converting to mesh or point clouds. Summarize about implicit data representation. First, they are very powerful. They can directly optimize the appearance with powerful deep learning methods without being constrained by the explicit representation. All we need is to optimize the observed images or videos. On the other hand, they cannot be used directly in the existing graphics pipeline. My intuition tells that there must be another way to use implicitly represented objects in VR. It is just as the humans who wanted to fly fast tried to imitate birds but failed, and an airplane that did not resemble a bird at all was the first to fly. It is important to think about what is really required. Our key hypothesis is that 2D renderer is enough or even better than explicit 3D models for data-driven 3D replication. Because it can directly optimize the observation, the visual error can be smaller, and the ideal 2D renderer can provide plausible but faster inferences for complex physics. We believe that there is only one requirement for 3D objects in VR, that is the ability to generate observation in real time, conditioned with the necessary information. Now, I will introduce our method and application. Our base concept is Billboard used in computer graphics and 3D video games. A billboard corresponds to a single 2D image that is tilted to always face the observer, creating an illusion of a 3D object. Billboards are often used for objects that look roughly the same from all directions, such as trees, grass, and flames. Based on Billboard, Deep Billboard is a combination of implicit data representation-based deep learning methods. By doing so, we have succeeded in pseudo-representation of 3D objects based on 2D image or video rendering without appearance degradation. As examples of Deep Billboard, we propose Nerf Billboard combined with the aforementioned Nerf, and World Billboard combined with world models to reproduce dynamic scenes. First, we introduce Nerf Billboard. Nerf Billboard is a combination of Billboard and Nerf that replicates 3D-aware objects by regenerating images conditioning to observer's viewpoint. Here, for real-time rendering of Nerf, we used plain octrees, one of our derivatives of Nerf. We converted 8 objects in the Nerf dataset to Deep Billboard. As is obvious, there is no deterioration in quality at all, and they can be viewed in VR as normal 3D objects. Next, we introduce World Billboard. While Nerf allows rich rendering of complex static objects, extension to dynamic scenes is still an active area of research. To show the versatility of our Deep Billboard system, we combined Deep Billboard with Planet, a neural state space model or world model for action conditional video prediction in deep reinforcement learning to achieve data-driven reproduction of time-varying objects from a single video. In order to use the world model as a renderer for Deep Billboards, we have developed a way to create a dataset for this purpose. We generate a normalized video and a series of camera pose data from a single video taken with the algo marker. With this dataset, we learned video prediction conditioned on the initial viewpoint image and camera pose series, and reproduced the time-varying 3D objects through the billboard in our VR system. This is a replicated doll. It's very cute. When you look carefully, you can see that this model is beating the drum occasionally. You can see that the appearance changes depending on viewpoint, creating the illusion of a 3D-like model. Unfortunately, the angle of the object sometimes shifts a little, but this can be cured by improving the video prediction method. Next, let me introduce Interactive Deep Billboard. A big disadvantage of a classic billboard is that it does not allow physical interaction. To solve this problem, we propose a system where a billboard is used for visual interaction while an invisible mesh for physics interaction. As shown in the figure, we used a mesh extracted from a trained Nerf model and realized some basic physical interactions. This makes our deep billboard to achieve both good visuals and good quality physics. I'll show you some demos. And of course, this system can handle multiple objects at the same time. Finally, I will explain the system of our method. Deep generative models such as Nerf or Planet require large computational power. So, we have built a system that uses cloud rendering to enable even inexpensive VR headsets to handle highly accurate pseudo 3D models as long as they have an internet connection. Each time step, the pose of the user's viewpoint relevant to the object is calculated from the pose of the user's viewpoint and that of the object itself. The computed query pose is sent to the cloud server for 2D frame generation, and the generated 2D frame is sent to the VR system. This system will work as long as video transmission is available. Therefore, in principle, deep billboards could be used not only with high-end computers and head-mounted displays, but also with smartphones and game consoles. Conclusion: we developed deep billboards for delivering real-world quality as it is. And we showed that replicating a 3D model with a 2D renderer is practical enough. Deep billboards can be combined with various deep learning methods, and this will be the basis of future VR technologies. Thank you for listening.